Hi, welcome to another session of Circuits and Networks. In today's class 15, we are going to see transient analysis of RL and RC circuits using Laplace transform solutions. So here you can see two different examples where the switching position is going to change from one point to another point, and we have to find out the solution for these kind of circuits using Laplace transform approach. So let us begin with the first problem. In the network shown in figure 1, the switch is initially at position A. On the steady state conditions reached, the position of the switch is moved to B. Find transient current I of t for t greater than 0. So we have to start with the solution. We can see 50 volts is going to energize the circuit to these passive elements. And how does it show its behavior when it is at position 1, that is at A, and then when it is changed to position B. So initially what we have to see, the conditions before switching. So at t equal to 0 minus, the circuit is shown in figure 1a. You can see here the switch was at position A and the steady state conditions have reached. Inductor under steady state behaves as short circuit, and the current which is flowing through 10 ohms and 10 henries, it is treated as I of 0 minus, which can be obtained with the help of I of 0 is equal to 50 by 10. Why? Because 50 is connected to 10 ohms and the circuit is closed and the steady state conditions have reached. So 50 by 10, which is equal to 5 amperes. So this we are treating as equation 1, and we know that current in an inductor cannot change instantaneously. So we need to remember that I of 0 plus will be also equivalent to 5 amperes. So this we need to keep in our mind before switching condition, right? Now the switch is moved to position B, and this is how the circuit looks alike. In Laplace transform approach, we need to understand that the resistor's behavior is not going to change, whereas inductor, which is 10 Henry, which will be equivalent to 10s, and L of I0 minus, L is the inductor value, which is 10, and I of 0 value is 5. So 10 into 5 will be 50 volts will be developed in the inductor. So this is the Laplace transformed circuit, and it is obtained from figure 1b. Okay, right. Now the current which is going to flow, which is will be treated as I of s, and that I of s can be obtained for t greater than 0 by applying KVL, which is equal to, you can see here you have 2, so 2 I of s resistor value, then you have 10, it's also resistor value, 10 I of s, plus here you have inductor. In Laplace transform it is 10s, so 10s I of s minus 50, the developed voltage in the inductor, and this we are treating as equation 2. Just take the I of s values in common, so we will be having 12 plus 10s, which is equivalent to 50. In fact, I of s will be equivalent to 5 divided by s plus 1.2. Here we have taken I of s and 50 divided by 12 plus 10s. I have taken the common terms outside, and that is how we have remained with I of s is equal to 5 by s plus 1.2. This we are treating as equation 3. Now just employ Laplace inverse to this equation 3. We are going to get I of t equal to 5 e to the power of minus 1.2t. This is the basic mathematics under Laplace transform, which we have framed, and we have obtained equation 4 using equation 3. So this is the general solution for the circuit. Now in question 2, we have the switch is closed at t equal to 0. So means what? The switch was open, naturally no current will flow in the passive elements. The steady state conditions have reached before switching, so that is all zeros. So we have to determine the loop currents, that is I1 of t and I2 of t for t greater than 0. So here once the switch is closed, we will form the two loop currents, and at t equal to 0 minus, as we know that the current is not flowing, in the passive elements, and once the switch is closed, the figure will be changed to like this. So the Laplace circuit, which is a transformed circuit of figure 2, it is shown in figure 2a. The 10 volts becomes 10 by S. You have 10 ohms resistor as it is. 1 Henry changes to S, 1S, 10 as it is. Again we have 1 Henry, so it becomes S, 1S, and 10 ohms as it is. So now we have framed two loop currents, I1 of S, I2 of S. Just we need to employ Kirchhoff's voltage law in order to find out the solutions for I1 of S and I2 of S. How do we do that? So first I am employing KVL to loop 1, that is this loop, and minus 100 by S according to the notation, plus 10 I1 of S, this 10, and again I have S here, so S I1 of S, because inductor we have to take the Laplace value as S I1 of S, plus 10 I1 of S minus I2 of S is equal to 0. I hope you understood how we frame the equation with the help of KVL employed to loop 1. So I'm taking the like terms on one side. So I1 of S multiplied with S plus 20, because you have 10 plus 10, that is why it becomes 20. And you have here S, so S plus 20 I1 of S minus 10 I2 of S, which is equal to 100 by S. So this is equation 1. Now applying KVL to loop 2, that is this particular loop, I'm going to get 10 I2 of S minus I1 of S plus S I2 of S plus 10 I2 of S is equal to 0. Again, taking the like terms and unlike terms one side, we are going to get minus 10 I1 of S plus S plus 20 I2 of S is equal to 0. Now from equation 1 and equation 2, with the help of Cramer's rule, we can find out I1 of S as well as I2 of S. So how do we find out I1 of S? So for that, we have to take the help of matrix equations by concentrating on equation 1 and equation 2. So I1 of S is equal to the determinant of, see you have in equation 1, you have 100 by S as one value on RHS, and equation 2 you have 0 in RHS. So I1 of S can be replaced with the help of the RHS values in this fashion: 100 by S and 0 minus 10 which we have obtained from this equation 1, so minus 10 I2 of S. Okay, and equation 2 we have S plus 20, so that is how we are going to get 100 by S, 0 minus 10 by S plus 20, and the determinant value of the matrix. So you have S plus 20 minus 10 S plus 20. You can cross multiply in the numerator as well as in the denominator. We are going to get 100 by S times S plus 20 whole divided by this S plus 20 square, minus of minus becomes minus 10 square. So this can be changed into 100 S plus 20 whole divided by this S goes to the denominator, S times S square plus 40S plus 300, because 400 minus 100 becomes 300. Now you can easily get the solution for S square plus 40S plus 300, which will be equivalent to S plus 10 and S plus 30. Now this is the equation what we can frame for I1 of S. Now with the help of partial fractions, I can change this value to this value. You can see we have 1 by S, that is A by S, plus a constant value 100, so that is B by S plus 10, and you have S plus 20. I can change the value as C by S plus 30. Now once I framed I1 of S as equation 3, with the help of partial fractions, I can obtain the values of A, B and C with the help of the normal technique. So for A, I have to multiply the main equation with S and I have to equate S equal to 0. With this, the S terms goes off and I'll be left over with 100 multiplied with S plus 20 divided by S plus 10 into S plus 30, and substituting S is equal to 0. I'm going to get 100 into 20 divided by 10 into 30. Here we have substituted S is equal to 0. With this, we are going to obtain the value of A, which is equivalent to 20 by 3. I hope you are well know with the partial fractions. Similarly, I am going to go with B. For B, I have to multiply S plus 10 and we have to remove the S plus 10 from the main equation and just substitute S is equal to minus 10. With this, we are going to obtain the value of B, which is equivalent to minus 5. Similarly, C can be obtained with the help of S plus 30 multiplied with the main equation, just cancelling out the like terms and substituting the S value equivalent to minus 30. With this, we are going to get the value of C, which is equivalent to minus 5 by 3. Just substitute ABCs in equation 3 and we are going to get I1 of S, replacing ABC with 20 by 3 by S minus 5 by S plus 10 minus 5 by 3 by S plus 30, and we have to employ Laplace inverse to get the solution of I1 of S, which will be equivalent to I1 of T. This 20 by 3 divided by S, Laplace inverse gives the value as 20 by 3 minus 5. Laplace of this value will be e to the power of minus 10t, and Laplace of this value is e to the power of minus 30t. So this is how we obtain the general solution with the help of partial fractions for equation 4 for this particular current. We can also find out the value of I2 of S, just replacing the I2 terms with 100 by S and 0, and the determinant value in the denominator as it is, whose value will be 100 by S into 10 whole divided by S square plus 40s plus 300, and this can be changed to 1000 whole divided by S of S plus 10 and S plus 30. With the help of partial fractions, I can obtain the value of A1, B1 and C1, like A1 is equal to S multiplied with the main equation, that is 1000 by S into S plus 10, S plus 30. We are going to take out the like terms and substitute the value of S is equal to 0, where the value of A1 will be 10 by 3. Similarly, the value of B1 will be minus 5 and C1 value will be 5 by 3. Now, this is the substitution what we are going to do with the help of A1, B1, C1 applied to equation 5, and then apply inverse Laplace transform to equation 5. I'm going to get the I2 of t, which is equal to 10 by 3 minus 5 e to the power of minus 10t plus 5 by 3 e to the power of minus 30t. So this is how we determine the solutions for transient currents for RL circuit. Let us go with the RC circuit. You can see in figure 3, the switch is initially at position A. On the steady state conditions reach, the position of the switch is moved to B. We need to find out the transient current IC of t and VC of t across 6 farads for t greater than 0. So with the help of Laplace transform, we need to find out the solution. For that, at t equal to 0 minus, the circuit has to be framed. So this is how the circuit will look like. In the steady state conditions, when the switch was at position A, this is removed from the main circuit and 12 farads is completely charged to 24 volts. And that is why V12 farads of 0 minus is equal to 24 volts. Since the capacitor acts as open circuit, the value will remain as it is as soon as the switch is moved from A to B. So that is how V12 of 0 minus will be equivalent to V12 of 0 plus, that is 24 volts. And we need to remember in our mind that no current is flowing through 6 farads. In fact, V6 of 0 minus will be equivalent to V6 of 0 plus as equal to 0 volts. Let us take this equation as 1, and with this analysis we are going to solve the rest of the circuit. So as soon as the position of the switch is moved from A to B, the capacitor, which is 12 farads, is completely charged with some voltage, that is 24 by S. The Laplace form of capacitor is 1 by 12S. You have 2 ohms as it is, and the capacitor 6 farad changes to 1 by 6x. Now this is actually seen in this form, that is 3B. In actual form is like this. We need to employ KVL to this figure 3B. The current which is flowing, which is IS, and the direction of the current assumed to be in clockwise, and applying the KVL. So minus 24 by S plus 1 by 12S I of S, this is the Laplace form, plus 2 I of S plus 1 by 6 I of S is equal to 0, and this we are treating as equation 2, and I'm taking I of S as a common, and on the right hand side we have 24 by S divided by the I of S value. It is taken in the denominator of the 24 by S parameter. So small simplification will give you the I of S value as 48 by S plus 0.5. Simple mathematics, you can cross over, and the actual equation of I of S is obtained as 48 divided by S plus 0.5. Now employ inverse Laplace to equation 3. We are going to get 48 e to the power of minus 0.5t. Now this is the general solution of equation 3. Also the primary requirement, and the secondary requirement is the voltage across 6 farads. So it is given by 1 by 6x I of S, which is equivalent to 1 by 6s times I of S value is 48 by S plus 0.5. Now with small simplifications, the equation changes to 8 by S of S plus 0.5, and this under partial fractions can be taken as A by S plus B by S plus 0.5. So this we are treating as equation 5. With equation 5, with the help of partial fractions, I can obtain the value of A, which is equal to 16, the value of B, which is equal to minus 16. Just substitute the value of A and B in equation 5. Then I'm going to get the voltage across 6 farads, which will be equivalent to 16 by S minus 16 by S plus 0.5. Just employ inverse Laplace transform to equation 7, and I'm going to get V6 farads of T equal to 16 of 1 minus e to the power of minus 0.5t volts. So this is how we determine the general solutions for transient voltage as well as transient current for RL and RC networks. I hope you like this video. Please share among your friends, subscribe to my channel, and please press the bell icon for the future notifications.